All right, so today in our class, we have only one lab to cover, and you can see the name called compression. And you will see the discussion today will be very, very similar to what we've done in the last lab. Remember, the last lab was about tension, and it means we're holding our specimen and we're trying to elongate the specimen. In today's class, we just have to reverse the force. So instead of applying tension, we simply compress our specimen, trying to make it shorter. Now, before I started the lab itself, you guys know, as always, I try as much as I can. If there are some photos I can show you so you know where this force will happen in our structure. So what you see on my screen is something called steel truss. Uh, and for steel truss under gravity load, the top chord, so this element here in the truss, we call it top chord, and always the top chord will be in compression. Also, those last diagonals which are going to the support, they are under compression as well. All right. The next example for you is something probably most of you have seen this scene. Okay, if you live in a house and the house has undeveloped basement, you see very similar picture where you see on the outside there is a concrete walls, and the main floor is framed with a steel joist. Okay, and because the span, the span is simply from here to the other side, maybe it's too big. That's why the joist cannot span. That's why they add this intermediate beam. Also, the span which is from here to the other wall is too big, and that's why they add these intermediate columns. Those columns, we call them telepost. Okay, so the telepost in your basement, and for sure if the basement is finished, you don't see any of this. Everything is covered, cladded. You don't see any of this. This is only for undeveloped basement. Even sometimes, or most of the cases, we hide those teleposts within the wall. So we simply sandwich the telepost with the wall, so we don't see them. But anyway, my point is, for this discussion, you can see here everything is gravity, so going down, and so you can see the joists are sitting on top of the beam, and the beam is sitting on top of the telepost. So this telepost will be in compression. This telepost will be in compression. And then finally, if you have any steel building, these columns will be in compression as well, all these columns, because again, as I said, for gravity load, where all the loads are trying to push down, the column will simply be in compression. Now, here we go. This is our test for today. The first thing I want you to know is what is the test designation. You guys know that we're doing the test according to some standards. And so we follow the American standard for testing material, ASTM. And for this test, the designation of this test is called E9. If you guys remember, last test was tension, and it was E8. E8. For this test, it's E9. And the test is simply, it's compression testing of metallic material, which applies not only for steel, but also for metallic alloys. Okay. Need to remind you, which this is not new, like you've seen this in the last, even we just talked about it in like a few minutes ago. We are not doing the test for the love of the test, okay? We do the test so we know how our material will behave under given load. Remember, when we say how does it behave, we need some numerical numbers, some metrics, and those metrics will tell us how it behaves. Those metrics are, you can see, I'm going to box them out for you, and that's our objective. Our objective is to find, for the material, we need to find what is the modulus of elasticity. We need to also find yield strength. We need to establish, okay, again, we need to establish the stress strain curve from which we can find those numbers. And then finally, we need to find the compressive or the ultimate stress, I need to use the same machine. If you remember, we had a machine called UTM. UTM stands for Universal Testing Machine. So the same machine that we use in tension, we're going to use it today in compression. Okay? All we have to do is just change where we place our specimen. Okay? But it's the same machine, no change. And so the machine, what it does, it applies compression like high force on our specimen. And so it also can measure the forces. And same thing, if you remember this name from last test called extensometer. And what it does, it measures the strain. So basically in our test, we're trying to establish the relationship between stress and strain by increasing the force. When we increase the force, the stress will increase, and we're able to record those. In addition, with the extensometer, we're able to measure the corresponding strain. So we're able to draw this relationship between stress and strain as we increase the force. All right, so let's get started here and show you the specimen. So the specimen is right here. That's my hand, and I'm holding the specimen in my hand, okay? Now, I have a question for you. Do you think this specimen looks like the one we use in tension? Any help?
No.
No, exactly no, because if you remember the specimen that we use for tension, it has a profile, and the profile looks like we changed the diameter. Why? Because for tension, we need to grip on the head of the specimen. That's why it's a must, no choice. We need to make the specimen the way it looks for tension. For compression, we're not doing that. For compression, you can see it is machined very clearly. It is machined. We have a clean surface, and the cross section is right here. So this is the cross section of our specimen. Okay, I'm pointing to the cross section. Why this important to point the cross section? Because simply our force will act this way. We're going to act by compressing on this face. We're applying our force on this face. Our specimen, roughly, the dimension is, so for sure, we will do accurate measurement, but it's roughly about ½ inch. So this is about ½ inch, which is 12.5 millimeters. All right, and also the same thing, this dimension is roughly about 12.5 millimeters, like ½ inch. And then the height is roughly about 2 inches from here to there. That is the height of the specimen, which is 2 inches, so it's roughly about 50 millimeters. I need you to remember that we are applying the force on this face in yellow. So if I ask you how much is my cross-section area, any help? If I ask you how much is my cross-section area, is it going to be 50 times 12.5 or 12.5 times 12.5? Any thoughts?
12.5 times by 12.5.
Thank you, sir. Because if we were to push here, if I were to push here on this face, then the cross-section area will be 50 times 12.5. Thank you so much, Masoud. All right, as I said, we need to do accurate measurement, and you guys know how we do that from previous test. We use the same caliper. You can see we have a caliper, and the caliper, as soon as we turn it on by pressing on this red button, it will simply give us the reading, which, as I said, it will be roughly around 12.5 millimeters. Okay, and you can see the specimen is machined. Okay, is machined. You can see when I did the measurement, we have to input them in our software on the computer, which is attached to our machine. You can see here, you have to input the width and the thickness. Okay, so think about this number as the thickness and the other one as the width. Doesn't really matter because simply it's square. At the end of the day, we have to multiply them. Can anybody tell me why it's important to input these numbers into the machine?
Because we need it for the stress or the strain calculation.
Thank you so much. Thank you so much, Masoud. That's perfectly said. Because the machine will get the force. The machine itself will read the force. But the machine cannot read the width and the thickness. That's why we have to manually measure them and feed them here. Once you feed them into the machine is able to multiply them together, find the cross-section area, and from that it can always give you the stress, because the stress is equal to force divided by cross-section area. Now let's move on to our setup. So here is the setup, and I'm not sure if you still remember how we did the tension. So the tension, we have, there is kind of a attachment or jig that clamps in onto the head of our specimen. For the compression, simply we have a different jig. So this black thing, it is the jig we use in compression. And so what happened is, here is our specimen. So this is our specimen right here, which is MS, it means mild steel. And so this on top of it is kind of a moving head. So this moving head, the machine will simply push right here. I don't know, the picture is not big enough, but think about it this way, the machine will push here. And this slides down. So the machine will push right here, okay? And so this head will slide down until it applies compression on the specimen right here. All right, remember also that we're not only measuring stress, but also we're measuring strain. So how can we measure strain? Anyone to help? How do we measure strain?
The strain is the changes over original length.
Yeah, but like how can we measure it? How do we measure it? You can see this device. So this device, anybody still remember the name? What is the name of this device?
What?
It's called extensometer.
Extensometer, yeah.
And if I zoom in here, probably you can see for sure. If you come to the school, you'll see better. But how it works is that it has a jaw over here, jaws, another jaws over here, and simply it clamps into the specimen. And then as this guy is compressed, for sure these points will move. And so this point on the metal will move down, and this point also on the metal will kind of move up. So kind of shorten, it shortens, and then our extensometer will measure this amount and then send it to our computer using this wire right here. Now I'm asking you one question which you will find on the quiz. If you guys remember, I said the height of our specimen is how much? Anyone still remembers?
50.
50. So from here to there, this is 50 millimeters or 2 inches. So this is 50. I'm asking you, can you guess what could be the height of the original length on the extensometer? Is it going to be 50 or less than 50? I'm going to move this arrow here and this arrow right here because this will show you where are the jaws. So I'm asking you the original length, which is right here. This is the original length of the extensometer.
Should be right less here. Than 50.
Exactly. So on the quiz, you will see this question. It will ask you what is the original length of the extensometer, and obviously it is not 50 millimeter. It is less than 50 millimeter. Hopefully this is clear enough. All right. All right. Now, you know what? Unfortunately, I don't have the video where I'm pointing my camera to the machine. However, I'm pointing my camera this time to the computer, which logs all the stress and strain. And I'm going to go to my presentation because I have a little video for you. I will run the video. All right, all right. Let's go here. So here is the video. Really, you won't see much here. We're not pointing our camera to the specimen, which is trying to break the specimen. However, as I said, I'm pointing my camera to the logging machine, the computer. And on here, you will see the development of the stress strain curve. Let's watch the video.
So
once it takes off, it'll tell me to remove it soon. Up to 200 MPa. Wow. Yeah, I think I gotta remove it here soon. Probably. I'm gonna take that off. Okay. I'm gonna set it like that. I'm gonna.
All right. So I want you to look at this curve and see what can you get from this curve. The black one, the black curve is simply the stress strain curve. The black is the stress strain curve. The red is the tangent at the start of the curve. And the blue is the offset at 0.2%. You guys remember when I go with the 0.2% along the blue and I go until this meets the black curve? What can I read here? What is my reading here?
It's a yield strength.
Thank you, sir. So the yield is very simple. You can find the yield by taking the intersection of the offset at 0.2% or at 0.05%, depending on whether you're testing mild steel or cast iron, and find the stress. All right. Now look at the modulus of elasticity. How can we find the modulus of elasticity, which is tricky? Any help on how can we find the modulus of elasticity?
It's between the red and the blue line. That's the slope.
The modulus of elasticity is the slope, okay? So
yeah.
Really the blue has no business, okay?
Yeah, sorry, that's a red and black. We need to find the slope on the black one. So that's the modulus of elasticity.
But my point here is that look at how the curve started. Look at 0, 0, and then what happens after 0, 0, and then looks like there is a little bit of less slope, then there is a higher slope. So my point is, when you find this, and this is something you will see probably on the quiz, if you see two slopes, are you going to find this slope of this line or the red line?
I know
that's not easy question, by the way. It's a difficult one, because simply why this happened? Why, like theoretically, the black should be go along the red. That's theoretically. However, I can tell you, due to maybe problem with the testing, the initial behavior has a kind of a slippage. Okay, so this slips. Maybe there is dust or maybe dirt on the surface of the specimen, or maybe a little bit of rust, where you get kind of a less strength. But then as soon as this is broke, what happens is you get the real behavior of our material. Bottom line is, when you find the slope, please find the slope of this line, the black one here. Do you see my cursor? Please find this slope, because this is really for the material, but this part here is because probably a little problem at the start of the test, kind of a slipping or slippage. Okay, so we're reading strain, not really. So this is really the slope of this line. This gives you the models of elasticity, not the red one. All right. Now let's go back and see what happened to our specimen after we finish the test, which is simply not. This is unlike tension. You guys remember what happened in tension? Remember what happened in tension? There was a necking, so there is a cross-section, smaller cross-section, and then there is a split. So our specimen split in the middle almost. How about here? Unfortunately, this doesn't happen in compression. There is no necking, there is no splitting. So you can see here we're applying compression. Probably I can switch to my PDF, okay? So probably it's easier to teach on PDF because I can easily draw an arrow. You can see here, this is our specimen after the test, and probably you can see what happened to our specimen. And this is maybe better, because what we did is this is before, and we applied compression. You can see our specimen gets shorter and the cross section gets even bigger. Okay, so we have sort of deformation, and I can tell you, we can keep pushing on our specimen until it becomes like a coin. So if we have a very strong machine, this could happen. We could end up with this situation. Okay, so losing all this height because our material is so ductile and it doesn't fracture, it just deforms. Okay. Now those are not new. Okay, those just a reminder for you on how we do the calculations. Remember, stress is equal the force in newtons divided by the cross-section area in millimeters square. If you are given the force in kilonewton, you just have to multiply by 1,000 to turn your force into newton. Also strain. Strain is the change of the length divided by the original length, and it's unitless. In the modulus of elasticity, it is simply the slope of the line, where you can pick any 2 points on the line. For example, I have like this is my line. I can pick 1 point here. I can pick 1 point here, and I can read for every point. I can read the stress, like go this way, read the stress, go this way, read the strain, go this way, read the stress, go this way, read the strain, and simply this is how you find the slope, which is stress number 2 minus stress number 1 divided by strain number 2 minus strain number 1, given that this is point 2, this is point 2, and this is point 1. Any 2 points. My recommendation for you is number 1, try to make these points as far as you can. Remember, it contains some sort of error because when you read these numbers like the 2 and the 1, you don't read them very accurately, correct? And that's why someone will say, okay, that's 175. Someone else will say 174 or 76. My advice for you to get the best value of the E, try to push these points as much as you can. As long as they are on the line, you get a better value when you push these points as far as you can. Now remember, the modulus of elasticity has the same units of the stress because this guy here has no units, okay? Strain has no units. So the units of the E are the same units as the sigma, which is megapascal or Newton per millimeter square, or finally gigapascal. Why gigapascal? Because the number is so big. I can tell you, for example, for mild steel, this number is 200,000 MPa, which you can say it's only 200 GPa, gigapascal. Okay, all right. Now this curve, just a curve for, we have never tested zinc, so we tested cast iron and mild steel. And to remind you, mild steel, because we have different chemical composition, mild steel has little carbon, while cast iron we add more carbon and silicon, and that's completely changed the behavior of the alloy. While mild steel has a yield, guys remember, this horizontal area of the curve, this line right here, this is called yield. This area here called yield. And after yield, we have a strain hardening, and then you can see, the difference is not like tension. In tension, because we're trying to elongate and we get nicking, so your curve will go this way. Because we get reduced cross-section area until failure. While here doesn't do the same thing. It goes like this, because as I said, we can turn our specimen into a coin. So if we have a very strong machine, we can keep pushing until it becomes a coin. However, this is not required, because simply, if this is a column in a building, what do you think? I'm asking you, think about this is not really specimen. Think about this as a column in the building. Do you think we can keep adding this and we call this failure? So the failure happens here or happens here? Which one we can call it failure? Do we have to really take it to become a coin like this? So we can call it failure? Not really, not really, because by that time, your whole structure is on the ground. So it's not really about the force, it's about the significant deformation. Is that clear? So anyway, so let's go to our curve one more time. Cast iron is not really very sexy, What happened is there is no yield. It just goes from zero, like the blue curve, and then finally collapse. Because cast iron is a brittle material, and you will see a fracture just like you see in the next slide. So anyway, Here we go. Here we go. So this is a specimen of mild steel before test, and here is after test. You can see there is no fracture. It keeps shortening, very ductile, and just to get a more cross-section area, right? How about cast iron? You can see cast iron. Cast iron is very brittle, and what it does that. It fractures at an angle of 45 degrees, which we call those ones shear failure. Shear failure. So really what I want you to understand from this slide is cast iron is a brittle material, so it fractures at a 45 degrees surface, while mild steel is ductile and it can take really lots of deformation. If you come to school on Wednesday, I will show you some samples I took it to the maximum. I kind of compress it so much, okay, without any fracture. Now here is a discussion, so we need to watch a video because I have an interesting discussion for you, which we will discuss after the video. So I have a video here I want you to watch, then we have a little discussion. The video is about compression. So we're applying here, you can see we have a specimen that we apply in a UTM, like universal testing machine, and we apply compression. Is there any significance between this specimen and our specimen, our test? So if I go back and show you our specimen right here, is there any significant difference between this column right here and our specimen?
It's longer.
It's a taller, okay? I mean, longer is okay, taller is okay, but watch how this can affect my results, okay? Let's watch the video and then we have a discussion. All right, so a couple of things I want you to notice is that look at the center line of our specimen. Is it straight? Is it straight?
No.
It's bending. That's one thing. That's one thing, and I'll let you why shortly. But also, I want you to look at the curve, okay? So the curve, this is the start, and you can see this same trend, huh? So kind of curve, and then it goes straight, and then it doesn't really follow what I was showing you a minute ago, like yield, and then it goes up, 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 up. So what is the difference between why it behaves differently than our specimen, our test? Those questions I will answer very shortly, but I want you to get notice of a couple of things. Take note of, number one, look at my cursor and you can see the center line of our specimen is curved, it's bent. While I'm not bending, I'm just applying compression, and also on the curve, I'm getting different behavior of the curve. Now we go back and I will simply just tell you the secret, okay? So watch this, please. Probably you have one of those at home, okay, which is simply a ruler, okay? Okay, you have these rulers at home probably. Okay, and look at this ruler, okay? So I'm holding my ruler here, okay? And then I'm gonna push, okay? Look at this, I'm not bending. Remember, if I do this, watch my hand, please. If I do this, I'm bending. And it makes sense. If I bend it, it makes sense if it takes this curve. However, watch this. I'm not bending. Look at my finger. I am just pushing. So why I'm pushing, applying compression? Why it bends? Because there is a phenomena that happens only in compression. And look at the name. The phenomenon has a name called buckling. Okay? So the members under compression, they suffer from buckling. Now, I need you to understand, but buckling is dangerous phenomena. Buckling is a dangerous phenomena. Why buckling is dangerous phenomena? Because look at this. Buckling is a dangerous phenomena because simply it introduces instability for our member, making our member curved. And you know what is the problem with this one? The problem is instead of me applying compression only, it becomes all of a sudden compression plus bending because my force is not going on the center line anymore. You can see that clearly. Huh? If I apply this compression, okay, the center line is bent and my force is not axial force anymore. It is axial force plus bending. And this simply will lead to the failure of the building. Okay. So if I don't take buckling into consideration in my design, this is what happens. I need to make sure that the buckling will not happen. Okay, and you will learn more about this one, whether with Corwin in class, or sorry, with Ramin, or even in the second year course for steel design. All right. So why our specimen? Why they have different curves? Why my specimen went one way? So you will see something like this. Okay. So the curve was this. That's for my specimen. While for the column in the test, it went this way. Because the thing is, on this curve, really on this curve here, because our specimen was so short. So I'm asking you, which specimen will be more prone to buckling? The taller one or the shorter one? Which one will suffer more from buckling? The taller or the shorter? Any thoughts?
The taller one.
Sure. How about the thickness? Look at this. Why the buckling happens? Remember, look at the ruler. One is wide, strong, and the other one is narrower and weaker. You can see here. Look at the buckling. Always will happen on the weaker, okay? On the weaker axis. So this is something you will know about it with the Ramin in the course called slenderness. It's not about height only or about cross-section area only or dimensions of the cross-section. It is combination of both. Something called slenderness ratio. This is something you will learn with Ramin. The more cylinder our member, it suffers more from buckling. Now, look at our member. Our member, look at this. I'm going to go back to our specimen and probably have some dimensions still. So when you think about the height is 4 times the thickness, okay? The height is 4 times the thickness. So think about it for now. Think about for now as this house cylinder, huh? So think about number 4 is cylinderness. It's not like exactly like this, but I'm going to give you some ideas about dimensions, huh? So the height is 4 times the thickness. Now I'm asking you here, okay, here for the video. If I scroll back to the initial, you will see some information about the column. I think it's right here. Right here. Do you see that? Do you see? I know that maybe you don't know what is HSS. It is 2 by 1, and that's the wall thickness, and the height is 26. So think about it, 26 inch, that's the height, and the smaller dimension is 1. So what's the ratio?
So 6 times.
26 times, not 6 times. The height is 26, and the smaller dimension is 1 inch. It is 2 inch by 1 inch. This is hollow tube. This is a hollow tube, okay? Hollow steel tube. So you can see here, looks like the ratio is 26 over 1, which means our ratio is 26. Can you imagine? We're testing in our test a column, small column, with a ratio of 4, while in the video it was testing a column of ratio of 26. Which one? So this number, the higher the number, it means my column is more prone to buckling. And that's why if we go back to our curve, on our curve, okay? So if I go back to my curve, this curve right here. Okay, you can see because in our test we have a very small. Our column is not cylinder; it's chubby, and that's why the failure happens here. Okay, while the longer or the taller or the smaller or the slimmer the member, the failure can happen anywhere on the curve. Okay, the failure can happen anywhere. Sometimes even it can happen even here. Okay, before yield. So sometimes it fails here, or sometimes it fails here, or sometimes there, or some there, depending on what. Can anybody tell me what are the main criteria that fails our column early? This ratio. This ratio. The smaller the ratio, it means buckling is not effective. It doesn't suffer from buckling, so it will be failure due to material failure. While if this ratio it is 100 or 150, it means your column is so slim, which means the failure of the column will not be because of the material failure, it's because of the instability of the member. Do you get this idea? So the failure could be due to the failure of the material or the instability of the column. The bigger the ratio, the slenderness ratio, which we said it's 4 for our test and it's 26 for the column in the video. The bigger the slenderness ratio, it means the column will become more subjective to more buckling. And because more buckling, it means more bending, it means it will fail earlier at earlier load. Does this make sense? So I'm asking you right now, is buckling good or bad? What do you think? Buckling is dangerous?
I think yes. Yeah, it's not.
Yeah,
good.
it doesn't. Look at this. When my column is short, I fail at very high load, very high load. When the column is taller and slim, it fails at smaller load. So buckling is dangerous. Okay, it's dangerous. Actually, we cannot avoid it. This natural phenomena. I cannot avoid it. All I have to do is just avoid it in my design. So I'm going to design my column in a way that will never see buckling. All right, with this, I'm able to finish the discussion for this lab. So what you want to do is right now, you want to take 10 minutes a break, 10 minutes a break. And then when you come back, please don't come to this channel. Do not come to this channel. Go to your breakout groups and then meet, please. Like, don't isolate yourself. Meet in group, turn on your camera, speak to each other, discuss the quiz, work on the quiz, and I will come probably after 30 minutes to check individual in every group. All right, any question for me before I let you go for a break? All right, thank you so much.